Great. Wonderful. I'll be talking about basically programming tools for dealing with electricity markets models. Some of you might not care about electricity markets per se, but I hope that the tools are still useful. It's basically mixed integer programming tools. And I'll be showing you some code with Julia as well that you have on GitHub. So if I will try to convince you that these are extremely important topics and it should be of your interest regardless. But at the very least, I do hope that the programming tools are still helpful, even if this is not your heart and soul, like it might be for me. Okay? So this is the plan. I'll tell you first about electricity markets and how they are interesting from a modeling point of view. I will talk about the many choices we need to make to model these markets that are otherwise extremely complex. And in other settings, we might have to do similar simplifications. The big difference with electricity versus other sectors is that in electricity, in many, many markets, we actually do get to observe everything and then some more. So simplifying is a choice rather than a necessity driven out of the data. But it is still a necessary choice. Otherwise, we cannot make progress on the questions that we are asking. So I'll talk about some of those decisions in how to simplify dynamics, how to simplify the models more broadly. I'll then give you two teasers of two papers of mine that are quite recent and that use these tools. Basically, that they combine short and long run dynamics with short run dynamics that are very, very high frequency and long run dynamics that are very slow. So how to combine the two. And then I'll show you the code. I don't know if I'll have time, but I was given the sense that it was encouraged to share code. We have an hour and 20 minutes, so I'm not a magician, as I was telling Rasmus, but I'll do my best. So let's see. Electricity markets. These are crucial markets. They used to be great even 20 years ago, but now I get to say that they are important, okay? So as you may know, we are in extreme need of reducing our carbon intensity worldwide, and we are not doing very well at all except for the electricity sector. That's where we are seeing some progress with renewable power kicking in, a transition away from fossil fuels, and many upcoming innovations in batteries and other technologies that are making it a very active, very lively market. So every year I have to change my slides because otherwise it looks like I'm slacking off and I don't care. And the slides are literally brand new. Go ask some of your other professors about some of their slides and when they were produced. It's very rare that the slides at the graduate level will become outdated so quickly, but in the space of electricity, things are changing very quickly. And again, in the space of climate change, it's one of the sectors where things are moving in the right direction. We have seen a lot of change in terms of adding renewables to the grid that bring up a bunch of challenges. And for those of you here at Wisconsin, Madison, you have Sarah Johnston, who's an expert on renewables. Dynamically, the batteries are helping a bit with the renewables. We have a lot of change also on energy efficiency and many ways in which the demand side is trying to become a part of our models, which usually was a very boring part of our models. That's also demand response. We are trying to actively get the consumers not only to be more efficient, but to also to actively participate. And one example of that is the electric vehicles and how households might respond with their electric vehicles, which is related to the last bullet point. The electricity sector is becoming very important because it's not only supposed to become decarbonized, to transition away from fossil fuels, it's also supposed to absorb the consumption of fossil fuels in many other sectors, including the transportation sector, which in many states is about 30 to 40% of CO2 emissions. So the electricity sector, again, is meant to do a lot of heavy lifting, and there's a big need for economists, engineers, and every other field that you can come up with to work on these topics. So that's my big picture motivation. So the problem of electricity markets is very straightforward. It's the typical Econ 101 market that we teach our students. We basically sort demand and supply, and we cross them in real time at every moment of the day. So it's kind of, I say, a straightforward problem statement, minimizing or maximizing welfare when you know the willingness to buy from the demand side and you know the willingness to produce from the supply side. You run the two lines and you cross them. I tell my undergraduate students it's one of the few markets in which not only we cross demand and supply literally at every point in time, but we also see the demand and the supply curve literally at every point in time. So we have infinite information of what's going on in these markets. Now in the simplest version, we cross demand and supply, but as you start getting into the details, the auctions in which we cross demand and supply for electricity are not nearly as simple. And for example, we have to deal with something that engineers call the unit commitment problem, the fact that the supply curve is really not a continuous smooth function, it's kind of a series of discrete steps. And that's what, again, they call the unit commitment problem. It makes it a combinatorial auction rather than just crossing demand and supply. So this is one example in which the auction was supposed to be a straightforward problem, and it's not as simple. Another example is transmission. There are not just one demand and supply, there's one demand and supply at every single node in the network, and the network can be a huge topological monster that as economists will have to simplify, and that will also make it harder. And on top of that, for many of the questions that we are asking about the climate transition, the energy transition, long-run investments matters, and these are at an extremely low frequency when compared to hourly data, so we also need to bridge that gap. There are also, by the way, some institutional markets that are at that low frequency. Those are called capacity markets. So if you want to look at everything that's going on in these markets, it's really very, very complicated. So what we need to do is basically simplify and model despite having better data, despite observing everything in the market, as I was mentioning. So sometimes if we are asking very big picture questions about investment, we might have to simplify our supply and demand model, and maybe the basic crossing demand and supply will be sort of fine. Or maybe not, and that's a research question. How much do we miss by not crossing demand and supply in a fancy way? How much do we lose by just being too simple? Depending on the question, it will be very clear that we need a fancier model. So for example, I'll tell you about a paper with transmission. Well, it would be a pretty bad paper if the paper is about transmission and the model does not have some topology. Although, as I will show you, we will make the topology very, very simple compared to reality. So we'll still make some simplifications, and that will be part of the modeling art in this type of papers. So as any structural model, there'll be data and code that will do the model, and then we'll get some output out of it. Again, the big decisions that we make in this type of setting is that typically the data does not constrain the model. The model constrains the data. Again, very different from other applications. And then another aspect of it is that we can really second guess a lot the goodness of fit because we observe everything. So if we observe everything and we don't put everything in the model, the goodness of fit will not be perfect because we could have done perfect. It would just have been reality. So we will have some challenges there, and it's important when we think about goodness of fit to see if we are getting the goodness of fit on the things that matter for the question at hand that we are trying to answer. And those are, again, challenging things. I don't have a clear recipe, but it's something to keep in mind that if the model doesn't fit some basic pattern that was our question of interest, then we should be worried about it. if the model doesn't fit some second, third order moment that we definitely observe in the data because we observe everything, maybe we're fine about it and we have to make those choices. So what are some examples of things that we need to choose that we could model way more complexly, but oftentimes we simplify? So on the supply side, we can make firms competitive or we can make firms strategic. And obviously, the complexity is very different when it comes to multiple equilibria that Victor was discussing this morning, when it comes to the notion of the equilibria that Ariel was discussing in the morning. The competitive framework will be much simpler. But maybe, again, depending on the question, it's good enough. We will also need to decide how accurate do we want to be about power plants. So in my thesis was very nerdy, and it was about power plants that turn on and off. So obviously the power plant was the unit of observation, but in many of my work, it's a technology firm. It's coal by company A rather than every single coal power plant that the company has, because reducing the dimension can be very important computationally. Same with geography. If a market is not particularly congested and you are not looking at transmission, maybe you can deal with it as a one market. But if your focus is on congestion or it's a market that's very congested, then maybe you need to put some more geographies. The no startup cost is exactly my thesis, what I was telling you about very nerdy behavior at the power plant level. After that, I have gone much simpler, and many of my papers don't have a startup cost. Instead, it's costly for firms to go up and down, but in a much more smooth way, which computationally, it's kind of a quadratic term rather than some non-convexity that makes the optimization way harder. On the demand side, it used to be very boring. It was basically either fixed or a little bit inelastic. Nowadays, it's becoming more fun because we have more and more smart meter data from households. So we now also have hourly data of households, and it's becoming a more important part of the model. For example, with electric vehicles, some people are modeling how electric vehicles are being charged in the grid in some monster models that have the demand and the supply side together. In terms of dynamics and more the temporal aspects of these models, when we think about the level of aggregation, we have to make choices on whether we keep it. For some of my data, it's 15-minute level data, but to be honest, I have never written a 15-minute level model because at some point I don't care. Okay. I'm fine with looking at hours, yes, even if I have 15 minutes. Sometimes we might want to look at daily. To be honest, for electricity, daily doesn't work that well, but we might find a way to aggregate things up to the daily level. Another aspect that's very important, and it makes life easier or harder, is whether the hours are independent from each other or not. Truth be told, they are not independent from each other, definitely not. But sometimes we might be okay just treating the problem as not dynamic at all. For most models, however, it will become dynamic. One example is what I was telling you, if plants have a bit of a hard time going up and down, that will make it dynamic. Another very clear problem for linking hours is batteries. I charge the battery when the price is low, and I let the battery go when the price is high. You have to take into account the temporal linkages. And when we are starting up plants, obviously, another important example, which is very relevant for the horizon of choice, is water. So water is, to date, the biggest battery to store electricity. You keep water in a dam, and then you let it go much later in the season. So for that, you might need a much, much longer horizon model. So what engineers do is when they do the water problem, they do a much simpler model, and then they bring it down in scale to more and more granular models, so that you can keep some complexity, but when you look at the hourly data, you actually are looking at a simpler model. So my husband is an economist and a physicist, and he tells me this is how physicists think about models. They have the atoms models, they have the planets models, like the celestial bodies models. So And the two models don't talk necessarily to each other, but there's some notion that they are related. But again, they use different tools, different modeling techniques. So it's similar in electricity. For day-to-day operations, typically we do 3 days, 4 days, kind of a short model. But if we are looking into water, we will use a simpler model that looks at weeks, seasons, and definitely if we're thinking of an investment model, these are extremely long-lived investments. We might have to look at 15 years or 20 years model. So it's a bit tricky to decide how to do these models, but it's part of the art of writing these papers. Let me know, by the way, if you have questions. So I wanted to talk to you about some dimension reduction techniques that we use. As I mentioned, the data as is are too rich in many markets. Some markets don't publicize data, but for the markets in which you can do work, the data are too rich. So what the engineers do is not very interesting, in my opinion. Many engineering papers are written on case studies, and everyone uses the same model, a very toy model with 9 nodes or 36 nodes that they put out. And then everyone, it's very good for the scientific process. Everyone tries out their models on the same thing, but it's not based on data. So what we do in economics is more data-driven than most engineering work. Not all of the engineering work, but than most engineering work. But then we have to make many choices, so it makes it a bit harder. And the scientific process is a bit more muddled with our choices as researchers. So when we do the historical data analysis, we have way more complex models than just a test case study with 9 nodes or 36 nodes. And then we need to, again, make some decisions. Depending on the question, if we are asking a very short-run question, we might look at a very short period of time because otherwise it's computationally too costly. But by and large, we want to work with larger samples. So I'll tell you about some machine learning techniques that can be used to reduce the size of these models that work quite well. So one example that I show you in the data is when you assume that hours are independent. This is a huge assumption. It buys you a lot in terms of simplifying the relationships of the variables. So it makes the optimization model way simpler to solve only by the fact that you assume that they are independent. But also it opens the door to finding representative hours that actually represent well what's happening in the data with much, much fewer observations. So imagine a data set with 83,000 hours, or maybe 43,000, I cannot remember. Let's say 43,000 hours. Well, what we will do in the practicum is convert that data set of 43,000 hours into 100 representative hours. Each hour will come with a weight, so it will be a representative sample, a representative survey of those 43,000 hours, and we'll get results that are practically the same as if we were to use the 43,000 hours. This sounds like magic. We made a huge assumption, and also the clustering algorithm will help us ensure that it's actually representative. So this is one example of dimension reduction. However, more and more, this dimension reduction trick is being challenged by batteries. In batteries, it's impossible, as I was saying, to assume that batteries are hours are independent from each other. So people are working on clustering techniques to see if they can extend them to batteries. There are some results out there, although more on engineering, on test cases at the moment. So when I do batteries or dynamic problems, then I cluster entire weeks of data, and I cannot go from 43,000 hours to 100 hours. Maybe I can go from 43,000 to several thousands. It still helps computationally, but obviously you cannot make such a simple, tiny model anymore. This is one example of clustering, but it can be used in many ways to deal with this data, and I'll give you some examples. So one example from my own work is to deal with smart meter data. We have smart meter data for another application of millions of households, and we observe them every single hour, their consumption patterns. Honestly, for a single household is not that much. For every household, we might have about 12,000 observations. But if you have 4 million households, and each of them you have 12,000 observations, it can become very slow. It's still doable, for sure, but it can become very slow to do analysis in that data set. So one thing that we do is come up with representative households and also weight them appropriately so that we have a much smaller sample that's representative of the patterns that we have in the data, but that don't necessarily keep track of these terabytes of data that are computationally too costly and that would make our model completely intractable. Another example is to deal with geographical granularity. So in Europe, markets are quite simple. Typically, they have one price for an entire country. And I love it as an economist from a researcher point of view, not as an economist from a philosophical point of view, because there should be several prices within a country. But it makes it very easy. In the US, there are, or Latin America for that matter, there are thousands and thousands of prices for a given market. So one approach is to pretend that the average price is the same in the entire market, and that might be okay depending on the question that you want to ask. But depending on the question, you might want to keep that granularity, those prices in the geography. But again, as economists dealing with a network of thousands of nodes that on top of that have very complicated relationships between them, the network in electricity, it's not a bilateral network. It actually has to follow some laws of physics, how the electrons will travel through the path of least resistance. So what we do is do clustering to find nodes that basically move together all the time. That means that within that cluster, there is no congestion, and it's okay to treat it as one region. And if two regions become separate, it means that there are some hours that are becoming too different, and then we need to make the model more complex. Here I put two examples. Ignacia Mercadal has a paper where she uses that to define the relevant market when it comes to competition. So if if firms are in the same nodal market, they are competing with each other. If there is congestion, they are becoming separate. I use it in my paper that we will see about Chile to basically come up with a 11-node market from a 1,000-node market. So much simpler. Other ways in which it can be used, sometimes to simplify heterogeneity. I was telling you that some models I keep every single power plant. Some models I only use technologies. We can use clustering to come up with representative power plants, similarly to make the model a bit more realistic, but still very low dimension. And another way in which we might be using clustering techniques or other sorts of simplifications is to come up with a state space that's manageable in a more dynamic model. So what are the dynamics that we have in electricity? We have the startup of power plants. I already mentioned that, how it's a non-convex, complicated problem. Probably an overkill. I wouldn't write a thesis on it again, but it was fun. The allocation of hydro, also a very dynamic problem, a bit medium frequency. So there are the relevant dynamics within a day, but also relevant dynamics across weeks. Batteries. For the batteries that we have at the moment, these tend to be high-frequency dynamics. So it's one day-to-day decisions that you're making of charging, discharging, charging, discharging. Divestitures, extremely low frequency, phasing out of coal. I'll talk about one of my papers there. And renewable entry, the other flip side of building stuff, also low frequency. So the techniques we will use in each of these papers are quite different, although they are all related. And they can all be framed as a constraint optimization problem, in a sense. But in practice, they are implemented in many different ways. Awesome. So some choices, I already mentioned this, level of aggregation. Are we thinking hourly, monthly? What are the relevant decisions that we're making? Are we thinking of a one-shot investment model versus a multiple period, more dynamic version of the model? Are we doing infinite horizon or finite horizon? What are the relevant dynamic variables that we can afford to keep track of? And what are the ones that we can afford to simplify? And then at a more IO level, do we want to make the firm strategic versus competitive, and how does it impact the dynamics and the feasibility of running the dynamics? For recent work, because the market is changing so fast, and the questions are so big. Oftentimes people do competitive frameworks that are simpler, despite the fact that strategic interactions are still important, but there are such large changes happening that we're trying to focus on the large changes and maybe not doing as much strategic work as before. The early electricity markets literature was very much focused on market power because the markets were relatively boring and very, very concentrated. Nowadays, the markets are way less concentrated and there are many things happening, so the focus on market power is a bit less strong than before. But that's how I grew up, in a sense, in grad school, learning about market power in electricity. So, do you have questions on the big picture? Oh, my last thing about the big picture is that almost always we will combine long, or not always, but often we will combine short-run dynamics with long-run dynamics. And the way we do that is basically breaking it into pieces, like a nested fixed point, where we have the outer loop, which is the big dynamic thing, and the inner loop, where it will be just 1 year of the electricity market. And we treat each of them quite differently. I'll show you in a second when I talk about the two papers. In particular, for the long-run one, uncertainty might be more important. For the hourly model, we do tend to simplify uncertainty because these models are quite deterministic, and uncertainty would make an hourly model blow up very, very quickly. So I'll talk a bit more about that. In terms of whether we assume they are recursive or finite horizon, traditionally in the hourly models, we also assume it's finite horizon because there's a lot of seasonality. So it's not quite recursive in any way. Monday is different than Tuesday, Tuesday is different than Saturday, and then June comes and it's different than August, and then Christmas break and whatnot. So everything is different, so we tend to model it again quite deterministically and in finite horizon. The year has 8,760 hours, we press play, and we see what happens in each of those 860 hours. If we want to put some stochasticity, we basically run different versions of that year, but we still assume that the firms don't treat that uncertainty as a strategic aspect. They basically, we solve the year, different versions of the same year to account for noise. On the infinite horizon, obviously the level of uncertainty is way bigger, and firms do think a lot about uncertainty in regulation. For example, Gautam and Ashley Langer have a nice paper on that. Firms think a lot about uncertainty on commodity prices, uncertainty on climate change. So for the longer run models, uncertainty is a much more vital question, and we take it more seriously. In that case, finite versus infinite horizon, more and more people are using finite horizon because it's such a fast-changing market that we know tomorrow will be totally different than yesterday. So again, this notion of the market being recursive in any way is kind of not very appealing at the moment. But back in the day, we were thinking this is kind of boring and will always be the same. But as of now, we do model it as kind of more like trending into a very clear direction with noise. Yes. Okay, so do you have questions on the big picture? Yes? As they could be. Yeah, I think it surprised everyone, including me, that I was working on this, and everyone. On the Chile paper, I'll mention that briefly, but it didn't make it into the final version of the paper, but we had a version where we computed what we see in Chile is that they invested in renewables too early, and then they became so cheap. And there's no way to explain it unless they didn't know that they would become so cheap. But guess what? No one knew they would become so cheap. So it makes total sense that they were not expecting this. One aspect that I maybe can say something more about is not so much the cost part of it that I think has surprised everyone. But I do think one thing that engineers underestimate a lot is markets and how markets are being adapted to renewables and how that lowers the cost of renewables. Not maybe the cost of building a panel, but the cost of using the panel and the value you get out of the panel. So I have a short paper that's it's not kind of a blockbuster paper, but I do think there are other papers in that area that could be done because there are many markets that have innovated in their design. So Germany went from trading, I told you I didn't care about half hours or 15 minutes, but Germany went from hourly trading to from hourly trading to half-hourly trading to continuous trading because of renewables. And that's lowering the cost of renewables in terms of market value, not so much the cost of the panel. California also convinced the rest of the West to join an imbalance market so that they can deal with last-minute renewable problems. And that has also lowered the cost of renewables. At the very technical engineering level, they are coming up with, I don't even know the proper engineering word, but they are coming up with things that you put on wind farms that instead of being harmful to voltage, they actually help with regulating voltage. And that's something that we had not thought about. So there are many innovations that are happening, but on top of that, they are very, very cheap. Yes, the panel itself, the solar is believed to be the technology of the future, and it actually has reduced discussions on other technologies like green hydrogen and whatever. Initially, people were very excited, but seeing how cheap renewables are, or even nuclear, people are like new nuclear or whatever, but if you compare it to the cost of solar at the moment, it's just very cheap, yes, and unexpectedly so, which is, again, some good news, we can use them. So, great, so I'll tell you about two papers of mine that use these type of techniques. The two papers are one looking at Chile and the integration of solar power in Chile with transmission, and the other one is looking at the phase out of coal power plants and the potential delay of this phase out given regulatory incentives in the United States. So I will not go in detail over the papers because otherwise I would not have time to give you all the material. But I'll do a bit of a teaser. So the first one is the Chile one, and I highlight here what are the features of the short-run model versus the long-run model. So the short-run hourly model for Chile will be either weekly blocks or monthly blocks, and we will solve the entire sample. So we will not simplify the data in that sense. The reason we solve 1 week at a time or a month at a time is that there is a lot of water in Chile on top of solar, so we wanted to account for the monthly dynamics of water. But we don't deal with the seasonal water problems in Chile. We assume that every month has some water, and you can choose what hour to use that water. That's the dynamic problem. But we don't consider shifting water from June to July to August. That would be another model, a complicated one. So we kind of pick our battles in that sense. I believe the final version is weekly because we had some hours, some weeks with extreme water shortages in Chile. And if we allowed for monthly shifting, it looked like Chile didn't have water shortages. So I think at the end we did the weekly one. That was our main model to be able to capture a scarcity in a better way. Otherwise, we were giving the model too much flexibility. So this is an example of choices that you end up making. The dynamics are water and also ramping, the fact that coal power plants are a bit slow in going up and down. And then for the transmission, that's a big feature of the model. It will have a transmission model. The good thing about Chile is that it's kind of aligned. So it will be a very simple topology, a line. And that does behave a bit like a trade model. It's the only version of an electricity market that will behave like a trade model. In the long run, the final version of the paper is very, very simple. It's a one-shot game where we see what's the long-run equilibrium, how much solar do you want to build in Chile. So it's a very simple zero-profit condition. This paper was revised for publication, so the first revision of the paper had a dynamic model, and then it went back to having just one-shot model. So the referees told us we needed more than one period, and then we did more than one period, and then we told them that said we didn't think it was necessary, and they agreed with us. So we went back to the one period. So when I was talking to my co-authors, I'm like, guys, this is something that we will do. And then they'll tell us it's completely unnecessary. And it's one instance in which I have managed to predict the future. Okay? So the other paper is more complex when it comes to dynamics, substantially more. So for the hourly model, we will do an annual representative model, which means that we take like a few weeks of the year, but we don't have so many hours, because otherwise it would be too many to make the model fast enough. It's also a model that the first model, by the way, it has barely any estimation, because we observe so much in electricity markets that oftentimes we barely have to estimate anything. So the only thing we estimate in the first paper is the cost of solar panels, which we have to estimate to rationalize the data. It comes out very close to the actual data of what a solar panel costs in 2019. But that's the only thing we do. When we had the fancier model, the estimation was a bit more interesting, because we had to estimate the beliefs of the firms and why they were investing at the time that didn't look good exposed. But it's basically almost no estimation. Here we have to do much more estimation, and therefore we also need to keep the model smaller, because the estimator will be a two-nest loop estimator, like a full solution estimator. So it has to be, it's not fast, but it has to be fast enough. We will have some ramping, although the easy way, with some quadratic costs of going up and down. And then the big decision will be that throughout the year, the decisions will be linked, because the firms will care about how much they use their power plant at the end of the year, so that they can show the regulator that their power plant is useful. On the dynamics, it will also be a fancier model. We will have the firms investing or divesting. The focus of the paper is mostly on divesting. We will have the firms divesting their coal power plants. And there will be some uncertainty, although limited. A lot of the evolution of the variables will be by finite horizon. The firms know what's coming. And on top of that, there is some residual uncertainty on commodity prices. So these are, again, the differences. And in both of them, again, these hourly models, if you put uncertainty, they become insane. So they will have no uncertainty in the hourly model. In my work during my thesis, for example, I had hourly uncertainty, because the whole thesis was about how firms decide to turn on and off in the presence of uncertainty. The way you do that in hourly models, I think I put it somewhere. I don't know where I put it. It's somewhere in the slides. I think later when I show you the tools. You basically run a few days, and you burn all days, and you only keep the solution of the first day. And then you go to the next day, and they look ahead, but you limit the uncertainty tree. You let it blow up a few days, and then you burn what's happening later. And basically that allows them to see the dynamics coming out, but not a full solution Bellman equation, because again, it's barely recursive for these models. And it would take many periods to be recursive. Yes. And with reasonable discount factors, 3 days are enough to capture all the dynamics that they care about for the high frequency choices. Great, so let me tell you about the first teaser. This is the one about Chile. So in this paper, we look at what happens when you build transmission lines that go into the Atacama Desert. So the Atacama Desert is this blue area in the first graph. It had very cheap prices because it had a lot of solar, but no one lives there. And the transmission lines did not allow to bring power to the north, which is a mining region. And while technically connected to Santiago, they were not making it down there because there was limited transmission. By the way, you're very, Andrea was an RA on this paper. So, now here we see two expansions, and we can see clear convergence in prices. The first one makes the prices between the north and Atacama converge, and the second one makes all prices kind of converge. So the initial goal of the paper was to do an event study around that thing and just see what are the impacts of the transmission line before and after. It's the perfect event study because one morning the system operator turns one button and those things are connected, and 1 hour before they aren't. So it's a very clear event study. And that's what we did initially. So we ran a regression on what the cost of electricity is before and after these interconnections to get a sense of the savings per hour that you get on the cost of energy. And this is what we did here, and we found that overall you saved about $3 per megawatt hour every hour. These might not sound like much, but these are average prices, so it's about a 5 to 10% reduction in prices. And depending on, if we look at all hours, this is the hours in which there is sun, kind of, and in the hours when there is no sun, it's more like a 3% reduction in costs. So we could stop here and do a cost-benefit analysis of this, but the highlight of the paper is, and we realized about it after doing the event study, is that we realized that we were looking at a very narrow event study. We were looking at before and after you turn the transmission line on, but many things don't happen exactly when the transmission line is open. Sarah has a paper about how difficult it is to build a wind farm. When you go into the queue, when they approve your wind farm. For solar panels, you can think about a similar process where you want to build a solar panel, but you cannot time exactly when the solar panel will come online. So in the data, actually, what we find is that many solar panels were already waiting for the transmission line. So if we do before and after, we're getting a bit of a confounded effect. We might get a huge effect from the transmission line because all those solar panels were already waiting, but we are not properly attributing the fact that the solar panels were there to the building of the transmission line. We are thinking they were there just magically. So that's why we use a structural model. In the structural model, we want to understand the red line is the solar panels that were built. We want to understand how many of these red solar panels that came before the transmission line were built in expectation that the transmission line would be built so that we can do a proper cost-benefit analysis. And that's why we do a structural model. That's where I come in. And we build a model of the Chilean electricity market to quantify the benefits of this investment effect. By the way, I agree a lot with Karam. So when we started this paper, Koichiro wanted me to do the structural model, and I told him, no, we do an event study. And that's where we started, but eventually we're like, oh, maybe we should do a structural model. The same happened to us with my other paper with Koichiro Ito. We didn't have the structural model at all, because initially I was like, no, we have a diff in diff in here, we do the diff in diff, and then eventually we saw some value to doing the structural model, so I kind of agree. I always tend to get there eventually, but I resist, and I'm sure it's the same for you. You always get there, but you pretend you're not getting there, yes? So, yeah, the model, I think it's very detailed. Again, the data are very good. And Chile, despite being a regulated market, it works in a very transparent way, and it has all the data that any other market would have. So we can treat it as a competitive market. The simplification of the network, this is what we did. We converted 1,000 nodes into 11 regions, and these regions are connected by a straight line, so it makes it quite simple. Hourly demand is observed, and for this model, it's one weakness of the model. We treat demand as given. The transmission line probably is also helping demand. It's providing welfare there. This is a project that we are now doing, trying to see if there are any demand effects, but here we shut them down. The supply function is based on very, very detailed operational data. And then the transmission model we built. Now the tools I'll show you today, it's how to do this. So if you have all these inputs, how do you convert that into an electricity market and how you solve for it? Here I put the baby version, which is minimizing costs, subject to constraints, and depending on how complex the model is, the constraints might be simpler or easy or harder. The simplest version is that the quantity that's produced by the power plants minus the flows have to be equal to demand and the losses, that the quantity of the power plants has some limits because power plants are limited, and that the flows have to obey some rules. This is the baby version, but obviously the models can become much more complicated. In our actual model, we have all the hydro constraints that you have to store water and you can drop it down. There are some limits at how much water you can use, and there are, again, several constraints. Our initial idea was to use the model from the system operator directly, and it was a model with 2 million lines. So we converted it into a model with much, much fewer lines. It's still a big model, but way, way smaller than what the system operator might be using. The dynamic part, actually it's not called dynamic, it's called investment part, because it's a one-shot model. It's basically finding the zero profit condition. So if you can build solar panels, how many solar panels will you want to build until you hit a zero profit condition? The assumption of zero profit is very reasonable because solar panels are very cheap to make, but also very deployable. So it's a very competitive market, kind of cutthroat. And basically the revenue we get from the model. So what we will be doing is looking at the model with more flows and less flows, depending on whether the transmission line is there. And we will see how the equilibrium condition for solar panels changes so that we can do a proper cost-benefit analysis. This is some more detail on the things we do. Again, for network, we do the K-means clustering. The supply curve is based on data, demand as well. The solar potential, oh, this is something I skipped, but we use NASA data to get at the solar potential of different places, and we calibrate it with the observed data as well. And then the cost of solar is the one parameter that we estimate based on the zero profit condition, which actually turns out to be very similar to the data for 2019. For 2014, 2015, sorry, I'm going the wrong direction. For 2014, 2015, the solar panels were way more expensive, and dynamically the firms should have waited if they knew that they would become so cheap. Great, so the bottom line is that the line is very beneficial, and maybe the more interesting part for our purposes of highlighting the methods is that the payback period for the line is very different, whether you think that these solar panels are falling from heaven or whether you take into account that these solar panels would not have occurred without the line. So we find that the payback period is about 8 years, which is very, very low for a transmission line that has a lifespan of several decades. But it's above 25 years if you don't take into account these investment effects, so highlighting why we need this structural model and why this might be something that you might want to do. So I think I put in here. In here, I put GitHub of my Chile project. You will not see much on this. It's too small, probably. But this is just to give you a hint of what we will be seeing. Here, we will have a huge model where we will define a bunch of variables and a bunch of constraints that will define our model. And then we will minimize the cost of producing electricity, subject to some flow constraints from the lines, subject to some quantity definitions, subject to some natural gas definitions, subject to some hydro definitions, and so on and so forth. From the market clearing constraint, the most intuitive one, quantity has to equal demand plus flows plus losses. We will get the shadow value of prices. So this model will also give us prices. By getting the dual constraint on the minimizing costs, we get the price of electricity. So don't worry if you cannot understand everything. You will in 20 minutes. So, great. Sorry? Yes. So the other paper I wanted to highlight very quickly, it has a similar flavor. It has long-run dynamics and short-run dynamics. The short-run dynamics are a bit more medium frequency. The interesting part, as I mentioned, is annual utilization. The firms have an incentive to produce with their power plants, basically to show that they are useful. Think about power plants being employees, and coal power plants are not doing well in the employee roster of the month, and the coal power plants are trying to show up and be useful. So that's what the model is about. The concern is that coal power plants are still sticking around a bit longer than maybe would be expected economically. And the question is how much of this could be due to these incentives of just keeping the asset going, even if technically it's no longer profitable. This is a big policy discussion, and in many states, people are discussing whether consumers are paying too high rates because they are bailing out coal power plants. And the bailing out of coal power plants is basically that you keep running them and you keep running costs on coal, even though coal is objectively more expensive than, in the case of the US, natural gas. Depending on the state, definitely more expensive than solar. The idea, again, is that we have a regulator in the model. It's a not active part of the model, but there is some regulation that comes from heaven and basically puts some incentives to the generators, the utilities, to produce, reducing their costs, so have some good incentives, but also provide some incentives to the utilities to keep using the coal power plant to show that they are still useful. I'll show you the equations in a second. So this does lead to some distortions. In the regulation economics literature, this is called the AJ distortion, the Average-Johnson effect, the fact that you have an incentive to keep some capital around or to overbuild capital. In our model, the firms will have an incentive to overbuild natural gas and to overuse coal power plants. Both of them not great for the energy transition because both of them are contributing to climate change. So the goal of the paper is to basically build a model to quantify these incentives. Identification, I can kind of say how the model is kind of identified, but it's thanks to the model, okay? It's a very parametric model. This is not something that we observe, like hourly data and emissions and power plants. It's a very tacit process between the regulator and the utilities. So identification is by the virtue of the structural model, yes. And our reduced form provides some, I think, semi-convincing diffs in diffs, comparing regulated utilities with non-regulated utilities, but still with a strong assumptions. So it's a very structural paper. This is the structure of the paper. Again, it's very parametric. So what we will have is that utilities get some returns on their portfolio, but they are penalized if they go over cost. This is the first term, that whatever their total variable cost is, it gets benchmarked against some cost, and it gets penalized if they get too much over the cost. This is to keep the utility efficient. But at the same time, this is where the distortion will come. They get paid for their capital, so they have an incentive to overinvest. And in particular, for their coal power plants, they need to show that they are useful. This is this U here. It's the annual utilization of a coal power plant. And if they don't manage to show that the coal power plant is useful, they will get a lower return on their asset. This is not literally how utilities work, but we think of this as a reduced form, kind of a structural reduced form, for the utilities not being able to invest in those coal power plants any longer. So if you have a coal power plant that's being barely used, it might be very difficult to justify doing some maintenance in it, or it might be difficult to justify bringing it up to compliance for some new regulations, for example, mercury regulations that were put in place. And then the utility will get paid for all of their costs, plus this allowed rate that depends on their capital and their return. So when we think of the long-run investment model, basically what we will have is that the utilities can invest in coal power plants. Divest. We actually restrict this, and it makes a lot of sense in this application. They can only divest in coal, and they can invest in natural gas, and they can do that in a continuous fashion. So the investment and retirement decisions will depend basically on the natural gas price, the capacity, that's the state of each utility. Each utility is independent, so it's a single Asian game. It makes things a bit simpler. And then some other things like demand, supply, coal prices, but some of these things don't belong to the state space, otherwise the state space would be too large. So we do finite horizon, and some things are predictable, some things are stochastic. Then within each period, the utility will earn the price of natural gas, which is the most volatile during the period. They make their decisions. Then based on all they know about that year, they will make their choices. And these annual profits are deterministic, as I was mentioning, and then they move on to the next decision. So a lot of the magic happens in constructing that profit, which has all these annual incentives to produce. It has all of these hourly decisions. And this is how it's determined. So basically, we will have an hourly model in which the utility will maximize their profit. And their profit will be maximized taking into account all the hourly constraints for the electricity market, plus the fact that the sum of all the coal generation will determine this utilization. So this is a quite complex model, and it can be solved either as a Bellman equation or it can be solved as a mixed integer program. Either way, it provides the same solution. I personally like more the mixed integer program because you can make it more precise. But with the Bellman equations, we have simplified the state space and then it's faster. So pick your devil. But at the end of the day, it's a full information finite horizon model, but that is very, very highly dimensional. And that it has this complicating constraint that the utilization is determined by all your decisions in every single hour of the year. So it's more complicated than your average hourly model. Estimation, again, it's a bit mysterious, I would say, although we provide intuition on how in our sample we have moments in which natural gas is very expensive and moments in which natural gas is very cheap. And that's what's providing the intuition behind the identification. We use indirect inference. So we estimate the model by feeding some parameters of the data, some moments of the data in regression form. We then run the model, and we run the same regressions, and we feed those correlations. Those are the most important moments in our GMM. It's a nested full solution GMM, so it takes quite a long time. For linking the continuous annual decisions to the hourly decisions, we basically estimate this profit function at a grid point, and then we fit a surface on this grid point so that we get a sense of what's the derivative of the profit function depending on my dynamic decisions. And based on those derivatives, we run the model again. So, and we do that for different prices of gas. So that's how we spend a lot of time in the computer creating these surfaces for different case and different prices of gas. And once we have those surfaces, we do the full estimation of the dynamic parameters. Yes, and that we have to do for different gases of different parameters. So it's a bit of a pain. Some of the parameters we obviously estimate only using the hourly data. So for ramping and some of these things, we can estimate it in a pre-step. That's what we do. These are the parameters. The standard errors look almost too good, but that's what they look like, at least so far. Pretty precise, given the model. We do have quite a bit of data, so that is helping, but pretty good. Although you can see that when it comes to the more dynamic aspect, the standard deviations are substantial. So, with the model, we do several counterfactuals. The ones that I will emphasize today, given the timing, is basically one in which we make the utility care more about minimizing costs, and one in which we make the utility care more or less about using their coal power plants. Our results, at least so far, we are revising the paper. I don't think this part will change, but let's see. Our results so far is that these incentives, regulatory incentives, are quite sticky given how we have set up the model. So even if we double the penalties or even if we make these utilization parameters matter less, it's very hard to approach a cost minimization approach. So basically, the regulatory setting is such that it's quite far from the first best. And even tweaking the regulatory parameters, we're still far from first best. As good economists, in the paper, we compare it to a carbon tax, and we conclude that we should put a carbon tax. I think you might have heard this story before, and it's also true in this model, that with a carbon tax, these parameters can do some more heavy lifting, and a carbon tax would be definitely necessary in these markets, but unfortunately not something we see so far. So these are the two teasers. Again, they are quite similar in the sense of combining hourly data to long-run questions. The long-run part of it, one is absurdly simple, and the other one is maybe not absurdly complex, but way more complex, okay? So these are, again, two examples if you want to look into them. I already showed you the code for that one. So now in the last 15 minutes, I guess I'll show you the code that you have on GitHub. I think I lied a little bit. I don't think you will get to understand it in the next 15 minutes, but I hope you get familiar with it, that you can go play with it if you want to. Okay, so that's the goal. So let me first go into these slides 1 second. So the tools I'll show you is the clustering algorithm to simplify the data. I'll go over it quite fast, but just to show you how amazing it is. And then I'll show you how to build a very baby version of an electricity model. The goal is not just to show you how to build an electricity model. It's very, very simple. But also to show you how to use mixed integer programming tools in Julia, which, my personal opinion, they are underutilized. I learned about mixed integer programming, I think in undergraduate, but mostly at the computational summer school in Chicago that Ken Judd used to run, and I'm still in love with it many, many years later. So it's very cool, and it has very good global properties. And it's very much used in electrical engineering. So this is why I got so in love with it. So what we will do is a very simple code of maximizing the surplus. DSE is confusing, it's surplus, maximizing the surplus in the market minus costs, subject to constraints. But again, I'll keep it very, very simple today. Okay? The one thing that I will not, important, the library we will use is called JUMP. It's basically a library for mathematical programming. Mixed integer programming is one version of mathematical programming with zeros and ones. But more generally, this library is used for optimization, constraint optimization, and it's very much used for building electricity models. Here I put you an example that's more engineering type model, but that you can look into it if you are interested in these topics. So what are mathematical models or mathematical optimization models? We'll have parameters, variables, constraints, objective functions. It's basically a maximization model that you write literally. Maximize f of x subject to x being some definition and so on and so forth, or x being larger than 0, whatever your constraints are. So it's literally writing your problem set in mathematical form in the computer. Importantly, it has to be a problem that you can write in mathematical form. So in many problems in I/O, I love it, but many times it doesn't work because our models are way more brute force. We cannot just write it as a beautiful max this versus that and subject to and done. So in many applications it doesn't quite work, but in electricity markets it's basically auctions are a maximization problem. So for the auctions of the electricity model, it works very well. So here I put a very important thing. In mathematical programming, variables are parameters and parameters are variables. So why do I say this? So when I think about econometrics, my parameter is beta, no? And my variable, no, wait a minute. Okay, now I'm getting confused. It's the opposite of econometrics, okay? So variables is what we are trying to solve, yes, and parameters are fixed. So the opposite of econometrics, where we want to know the parameter. Okay, so that's it. Yes. There, I said it. So variables is what we are solving for. It's not x and y. Okay. It will be p and q. So imagine you are solving a Cournot model. You know the slope of the demand function. You know the marginal cost, and you are trying to solve for p and q. Okay. So the nice thing about this type of modeling is that we write our optimization model, and then we can say which solver we want to use to deal with it. And we can even try different solvers by making very small adjustments to the code. So it's kind of a nice feature of this, that it's not very hard-coded to a particular solver. It's also a downside. It's not very hard-coded to a particular solver, so maybe it's not the most efficient way that you can do this, but you can do it quite quickly and in a very transparent way. Okay, so that's a summary of in my opinion, some advantages. It's easy to read and debug. It's trivial to build models with many variables and dynamic links. It's possible to work with global solvers depending on the nature of the problem. But there is also a large literature on how to frame your problems to be able to talk to those solvers. So that's an interesting part. And without uncertainty, it allows for a very parsimonious description of the data without much need of simplification. As you add uncertainty, these do blow up very quickly, as they do in life, and therefore it might be not feasible. This is where I put the solve and burn strategy that I was mentioning, where you look ahead a few periods, but then you burn it, and then you move on to the next period, because it's not feasible to fully integrate the future. And with a discount rate, even if it's very close to 1, with hourly data, very quickly you run out of relevant periods, and you can burn them. I will not talk about this, I think, but here I was emphasizing how to convert the basic model into a mixed integer programming model, and using M formulations that are used in engineering and electrical engineering. I don't think I will get there, but it's in the code. Okay, so let's go into the code. So in GitHub, let me see, in GitHub, you will find, let's see, where is it? Here. You will have the practicum, and basically it's not very clean. Everything is in one folder, and in the code you basically will set up your dir path to that folder, and it will work. Okay, so it's not very tidy, but it will work. How many of you have coded in Julia? Oh wow, a lot. I guess there is selection. Amazing. Yes, very cool. Okay. So yeah, most of you know what Julia looks like. This is Jupyter Notebook using Julia. I add a bunch of pretty standard packages here. The clustering one is the one we will use to cluster the data. I think I used Julia 1.10, by the way, and it worked in my computer. As you know, Julia can be a bit, mysterious sometimes, but it works in my computer. So the data I provided is about, 43,000 observations of several years of data. Every year is 8,760 hours. So here we have several years of data. It's very simple time series data. So we have for every year the price of that hour, the imports that went into California in that hour, the quantity consumed by different levels of households, commercial, industrial, residential, the potential wind, the potential solar for that hour, and the hydro and nuclear production of that hour. This model will be very simple, so we will take hydro and nuclear production as given. So no interesting dynamics there. So what we will do first is convert this into a tiny data set. Instead of having 43,000 hours, we'll convert it into 100 hours. And this is a very simple procedure. Basically, what we will do is select the relevant variables that we want to use for the clustering. Here I will use all of them, the price to the hydro and nuclear power. Obviously, I will not use the day and the month and the year, because that's precisely what I want to cluster. But I will not even use the hour of the day. So I will really simplify the data and just cluster on price, imports, and these other variables. my experience, very important to normalize the variables before doing the clustering. Otherwise, some variables will drive everything. I put some randoms in, not a very lucky one, but 2020. And then I get the clusters, okay? And we went from a data set of 43,000 observations to one of 100 rows. It's a bit embarrassing, but it works. And then we bring it back to a data set, basically a data frame, okay? The very important variable in this data frame is this weight here. It's telling us how many hours are supposed to be represented by this one cluster. So this one cluster is supposed to count for 287 hours. So without the weights, this would definitely not be representative. Yes?
How do you decide the number of clusters for the paintings?
So this was a paper that was a very stylized paper. It was mostly a theoretically inspired paper. And I was also about to give birth. And it was an invited paper that I had to submit before giving birth. So I went very low on the clusters so that the code would run faster. And then after giving birth, I checked that if I increased the number of clusters, the results would not change. So that was a very scientific process. Like more seriously in practice, I would have done something much bigger for an empirical application. This was basically a conceptual paper. And honestly, the results don't change if you go from 100 to 500. So I felt pretty confident with this. For the Chile project, we started with clusters of weeks. And then for the full paper, we wanted the full data, and we'll let it run and simmer for the entire data without any simplification. So, but for this paper, I thought it was enough. But it was a very constrained optimization I was doing there. And again, for the purposes of the paper, it worked, yes. But usually I try to be a bit more scientific. But I did check for this paper that the results didn't change. This paper, what I will show you today, is extremely simple. But in this paper, it was a paper motivated by Ramsey pricing and whether you should charge higher prices to residential households, which are more inelastic, rather than industrial households, which are more elastic, going to very basic Ramsey taxation questions. And despite the model being so simple, I actually had to compute the optimal Ramsey prices. And it took quite a while to do that iteration on the optimal prices. So that's why I went for such few clusters if I need to give a more scientific version of the matter, yes. But yes, sometimes it's computational choice, but I always check that if I push it a bit more, I don't get wildly different answers, yes. This is a model without dynamics, so it works. For models with dynamics, this wouldn't work. So here you can already see that the cluster data looks very similar for prices, for example. It's the same distribution. But importantly, also for solar. Solar panels have a weird distribution. It's bimodal. It's either night, and you get 0, or some sort of a normal kind of looking distribution. And obviously, it doesn't quite fit the data. The clusters are much fewer. The original data is much smoother. But it's kind of enough to reflect the production of solar panels. In the paper, I also show the correlation matrices of the original data and the correlation matrices of the clustered data. And the correlation patterns are captured actually very, very well. So at the end of the day, given the model, this is all that affects the model, and maybe it's not as surprising that the results are quite similar. Yes, but it was a bit surprising at the time that with 100 clusters, I could kind of get away with murder. I cannot remember if the final version of the paper has 100 or 500. Yes. So what do we miss from this? Well, we don't, in a regression model, we cannot put fixed effects. We no longer can do a two-way fixed effect model because there's no notion of years, there's no notion of hours. So you do lose a lot, but in a model, in a regression you use a lot, but in a model, it's still quite good, okay? So here I save the data as GRE journal clustered 100, and this is what we will use for the other code. So let me go into the other code. Can I get 5-minute extension? Yes, 5-minute extension, yes? Yes. So I provided 2 more additional codes, and again, they are very, very simple, but it's just so that you can actually understand it, okay? It's what I use for teaching at a master's level, not even graduate, but I do think it's useful to have code that you can understand. So this simple model will be basically building a model where we maximize, let me go down there, where we maximize consumer surplus minus costs subject to a bunch of operational constraints. This is the nonlinear solver version. Why is this nonlinear? Well, despite assuming that demand is linear, this is what this is doing, is fitting the demand curve to be very, very simple. Despite assuming demand is linear, the consumer surplus will be quadratic. So there will be a bunch of quadratic terms. And here we will be using a nonlinear solver to basically solve for the social planner, maximizing consumer surplus minus costs. Okay? So how does it look like in JUMP? In JUMP, basically, we build models. And here I called it model. Oftentimes in sample code, it's simply called M. You could also call it my model or nothing that has model in it. Okay? But it's basically a model that calls a particular optimizer. Here I will be using iPopt because you can use it directly in your computers. I absolutely do not recommend it for research, but it's freely available. I think if you do research, you can do better with some other solvers that are commercial, but that are available for free to academics. I put examples here in the top. I put Gurobi and Ciplex as two examples, or Nitro, for example, of solvers that you can use with an academic license. But for today's code, so that it can run immediately in your computers, we will be using iPopt. This is as easy to change. So I do have Gurobi in my computer. I could change it to Gurobi. I would have to change some of the options, but the model would still run. So how do we build these models? We declare the variables that we are trying to solve for. Remember, variables is what we are trying to solve for. And we just put them in the model. So in this model, I want to solve for prices, which go from 1 to t. Here, t is 100. I want to solve for demand, I want to solve for imports, and I want to know what each technology will build. Notice that the indexing is very nice to do in this type of programming. I previously had coded mathematical programs in MATLAB, and I had to keep track of huge matrices. It was a mess. This makes it very simple. Now MATLAB has also improved, okay? But back in the day, you had to program a huge matrix and keep track of all the indices. Here, you can just do it very nicely. And then it's very simple, as I told you, it's like taking pencil and paper. We write down the objective function, which is maximizing consumer surplus, which is this thing here. It's a triangle and a rectangle, minus the cost of production. And that's it. Now, if we did that, we would get that we could get infinity because there's nothing disciplining the model. So what are the constraints to the model? Well, demand has to be equal to the function that we specified it's equal to. Imports have to be equal to the function that is determining imports. And more importantly, demand has to be equal to supply, which is the sum of the quantity of all technologies and imports. Notice here that the notation is very simple. So if we want the quantity to be equal to the demand in every hour, we just put the index here, and it works very nicely. And on the supply side, quantity has to be below the capacity of every technology. For wind and solar panels, this is an input to the function. We can decide how many solar and wind to build with some default options. And basically, we have to use wind and solar according to its available capacity. And how do we solve the model? We just press play, we optimize, and we get the result. And if it's locally solved, we get the output. And if not, we kind of let you know that it did not solve, okay? So let me see if this is in my computer. It should be. Let me see if I have it there. So then I would run the results, and this is what I get. I set it up as a dictionary. Oftentimes I set it up as a data frame because I run many, many models. And basically I get that the average price is this. Now we could ask, okay, what happens if we build a lot more solar or a lot more wind, and we put 20 gigawatts of wind? And in this model, we would find that, wind gigawatts, maybe like that. we would find that the price would go down substantially because wind is cheap and it's bringing prices down. The cost to the system would also go down very much, particularly because I'm making wind free in this model. In the next notebook, we actually decide how much wind to build. Okay? This is the goodness of fit. A bit by construction, given how the model is calibrated, there is very good fit on the demand. And then we can do a bunch of experiments. Here I put another one. Now, this is a social planner problem. In the code, you have the mixed integer solver. And the nice thing about the mixed integer program is that it relies on first order conditions. So you can put the first order conditions for the social planner, but you can also put the first order conditions for a Cournot model with market power. It's in the code if you are interested. Okay? Last advertising is about the model Invest one. And it's embarrassingly simple, but I basically will do the long run model on top of this. Because the model is so simple, we can do it directly in this model. I was maximizing consumer surplus minus costs. I could add investment in that model, and it would still run. Because it's a very simple problem. In reality, most times it wouldn't run, but here it would be trivial. I can also solve for the zero profit condition that I will put in there. And I could also solve it as a mixed integer programming. The mixed integer programming version is interesting intellectually, but in practice I have found myself that for the real models, it's better to do the two loops, like the outer loop as a separate thing rather than trying to do everything at once. But the code will show you how to do that. It will show you how to do the basic zero profit condition that gives you an answer of 3.24. The basic social planner maximization that gives you an answer of 3.24. And the mixed integer programming that did a lot of heavy lifting to just get at the same answer of 3.24. Okay, so that's in the code, and I hope you enjoy the code. By the way, some more advertising. If you're interested in these tools, this code is part of a broader set of codes that you can find here. These are the same thing, a bit digested with the slides and some other background on readings. And there is this bonus one with a bunch of other models that you can find in JUMP, most of them in JUMP, I think.